Good morning, good afternoon, actually, even good evening, wherever you are. Welcome, and thank you for joining us today. My name is Michel Chabreau. I am with the Product Management Senior Leadership Team here at Wind River, and I'll be hosting this session about robotics and the era of artificial intelligence and autonomy. So, for the next 40 minutes or so, I'll be talking about some of the advances and technologies, specifically around AI, compute, and others, that are actually bringing a wave of changes into the world of robotics. Specifically, we'll look at some of the drivers, so some of the reasons behind this changing being brought into this market. From a technology point of view, what are some of the solutions? What are the challenges? What are the things to consider? I'm pretty sure you understand that security is obviously going to be one of the topics we're going to have to discuss. We're going to look also at where and how AI is being used in this environment. So there's going to be a broad range of things. If you have any questions, keep them for the end. We'll have some time for that. It's part of the plan. So let's get going. So what is a robot? Well, a robot is a machine. That's simple. According to the Oxford English Dictionary, it is a machine that is capable of carrying out a complex series of actions automatically, especially once programmable by a computer. So complexity is a factor, autonomy is a factor. Autonomy is a term that is used differently depending on the industry, and there are various levels of autonomy. But it's something that is fairly intuitive. If a machine can do something on its own without a lot of human intervention, we can easily reference and understand what it is. Okay, so this is for our machine, our robots. The second key definition is artificial intelligence. This one is a little bit more complicated. There are a variety of technologies, underlying technology that drive a little bit what AI is. So we'll try to use a simple definition. So that kind of AI, artificial intelligence, refers to the simulation of human intelligence in machines. And that seems to be extremely broad, but it's for the purpose of being able to mimic human actions. I think we can agree that this definition will help us a bit. So we're not saying the machine starts creating paintings and will replace Shakespeare, but the machine is able to perform actions that are not directly programmed. In other words, it's not if blue do this. We're actually going to train the machine to have a behavior that is similar to that of humans. Okay? So what happens when you mix robots, machines, with artificial intelligence? Well, you get artificially intelligent machines. That sounds easy enough, right? So these machines are actually similar to their peers, except that the control functions are no longer pure logic written by a human being saying, if A then B, if C then D, etc. It is driven by the technology that is driving AI today. So it opens up a lot of new doors and a lot of avenues for a variety of applications in a variety of industries, including, in airport, right? Look at this little airport you can see in San Jose. You also have some could be used for food delivery. It can be used also for research in a lab, helping out scientists during manipulation. So these machines are actually a new breed, if you will, although you can still look at them as machines, but it's a machine that has new potential, and that new potential is disrupting a lot of things. It's disrupting our lives, it's disrupting businesses, and is bringing a whole lot of opportunities. So at this point, you may ask yourself, well, what's the market view here? Is there a global line of thinking, if you will? So for that, I'd like to bring two data points for your consideration. The first data point is a big number, $14.3 billion. So that number is the expected valuation of the global smart robot industry in 2023, according to Business Wire. And then you might look at it as, okay, it's a big number, so what? Where it matters is where it was in 2018. So we're trying to look at where it's going to go. But in 2018, it was at $4.9 billion. So if my math is not too off, this is almost a tripling in market valuation over 5 years. That is what is astounding. So that's almost a 24% growth year over year over 5 years. That is the first data point. The second data point that I wanted to bring up today is more of a piece of information, but it is still fairly interesting. The NASDAQ is tracking the industry outlook for artificial intelligence and robotics. And they have an index, the CTA Artificial Intelligence and Robotic Index. And that index is there to provide exposure to the 3 stages of the global AI and robotics market. And so these companies that are part of that index are classified as either enabler, engager, and enhancers per the Consumer Technology Association. So enabler are about 25% of the total, and they are the ones providing the foundational, the building blocks, all the underlying technology. Then you have engagers, which amount to about 60%, and they design, create, make products, software systems. And finally, the enhancers that are about 15% of the total provide their own value add on top of these technologies. Okay? So this is great, right? The market is growing. The NASDAQ is tracking, so there's ways to figure out where we are. But still, you might tell yourself, this does not apply to my line of work. Well, today at a macro level, everybody is impacted. So this is not a matter of, whether or not you are, as the industries, the various industries are impacted, whether it's aerospace, defense, medical, transportation, manufacturing, any form of automation, obviously. Think emergency services, freight, right? All these markets are looking at ways to leverage robots and AI to improve the services, to make sure their products are better. So everybody is impacted. So you might still not 100% feel like you're being impacted, but look at it a little bit from a macro level. Let's start by us, people. You, me, your family, your friends, your neighbors, your coworkers. We as people have some needs. We like to have better things. We want a new phone, a new TV, a new car, to improve our quality of life. This is a fundamental driver for a lot of the things we do. We want to improve our own conditions. Sometimes we want to make statements that could be about being good for the environment, putting solar panel, we're creating wind farms. We also want to reduce our exposure to dangerous jobs if we can avoid it. We want to avoid doing dull and repetitive tasks. All of these are basic human needs. This is the society as a whole. As a society, then this kind of feeds into the industry that is still made of people. And these industries decide, well, I want to serve my customers. I want to help them get these better things faster. And so these industries will start optimizing their processes. They will start making these better things faster, just like we at Winnover try to do, right? We want to help our customers make better software faster. So this process are going to demand some innovation, some business transformation, some new services. This in turn will push the rest of the industry to innovate and create new technologies. And the current technologies that are relevant to this particular session are going to be about compute at the edge. There is more and more compute at the edge. If you look at the compute power of a phone today from that of a phone 10 years ago, this is night and day. Number one. Number two, you will have ubiquitous connectivity. Today, it's not exactly there yet, but we're getting there. 5G is a transformation shift for our industry. So you will have now with this compute and this connectivity, you also have a significant amount of data that is being generated. As a matter of fact, an enormous amount of data. So there are some numbers floating out there. One that comes to mind is one from the International Data Corporation that predicts that the amount of data in the world will grow 10 times by 2025 to 163 zettabytes from the 16.1 zettabytes of data generated in 2016. So there is a tremendous amount of data that's going to be generated, and we're going to talk about it. Now, if you combine these, right, you have compute, connectivity, and data. Data drives AI. So this is kind of the perfect storm to bring these new technologies and these new robots that are going to satisfy us as people. And in turn, we're going to push the businesses again, and the technology is going to continue improving, and around we go. Okay? One of the key pieces in the equation is data. You probably had guessed it. Data feeds artificial intelligence, which requires compute and connectivity. So this is definitely the key piece. Today, robots are generating a lot of data, and they're generating this data primarily from their sensors in order to operate. Sensor input is a key data generator for the purpose of a machine to operate. The second type of data that we see being generated is more for the purpose of operating the business. So they are data that are going to be used to provide services. Predictive maintenance is one of them. Monitoring, obviously, wear and tears being part of it. Power consumption, number of units produced, looking at the efficacy and the effectiveness of the process, and all kinds of other metrics that are relevant to a particular business. That data will tend to be consumed not by the machine itself. So I believe that with Cisco had this number, they were predicting there would be 850 zettabytes of data created outside of the cloud by 2021. So I'm not too sure actually where we are today, but the number is certainly very large. So what are we going to do with all that data? Well, we'll have to consume it somewhere, push it somewhere else for consumption. And it can be consumed locally or relatively locally, and it can be consumed remotely, pushed to a cloud. What binds data and connectivity, at least logically from a software point of view, and maybe even hardware, is going to be security. Security should not be a design option. It should not be an afterthought. It should be part of it. And I know that many times we have to make a decision is, can I afford securing my device because my footprint goes up? It's reducing my performance, or it's increasing my cost because security is complicated. So all these questions are very valid, but this should not really be something you can discuss or debate. Imagine the cost of a standard software bug, silly defect, something you have in your software. If you had found it during development, it would cost you X. Now the device has been fielded. Your robot is in the field, and your customer finds the issue, calls you. The cost of fixing that defect is much higher. And the same logic applies to security. So don't trade security for something else. And somebody much wiser than I am told me once, it's not about if, it's about when it comes to security. So you may think it's a hyperbole, maybe, But look at 2019. In the first 6 months of 2019, the number of attacks on IoT devices tripled. If you look at the number of security breaches in the last 5 years, they increased 67%. As a response to all of this, the cybersecurity budgets grew, and half of these budgets is now allocated to security services. And you might wonder, why are we doing all of that? Well, it's because when you are under attack, and I consider this to be an attack, in 71% of the cases, these attacks are financially motivated. In other words, somebody wants money out of it. Today, classic and common one is ransomware. The medical industry has been heavily impacted for that, obviously financial industries. But then financial motivation can take a lot of forms. Stealing your credit card number is one thing, but you might have bigger gains by just blocking some controllers in a water treatment facility and demanding money. Otherwise, you damage the system. So there are a bunch of criminals out there that are becoming very ingenious when it comes to leveraging devices for the purpose of making money. So again, do not ignore security. So let's look at our data. Let's go back to our data. I just mentioned that a lot of data is being generated by the robot. Well, just to be clear, a lot means 75%. 75% of the data that is going to be generated is going to be consumed at the edge. 3/4 of it. The key point here is not so much that 3/4 is going to be consumed at the edge. The key point is we need to be able to consume the data, but not at the expense of the key features of the machine, its DNA. That DNA could be its determinism, the ability to process events in real time, its footprint. There's all kinds of other aspects that will vary from industry to industry that will need to remain true. So the question is, 75% of the data is at the edge, but what kind of data is that? I mentioned earlier sensor input. So that data is probably going to be always consumed at the edge, but some of it may actually be aggregated and sent to the cloud for further analysis. So operational sensor information is likely to be consumed at the edge and it will remain local. Supervisory and controlling type of data will also remain local. And obviously all the data that is related to machine to machine communications. And think about AI. What if a machine with AI learns something? And we say learn. It's not like it suddenly is going to start speaking Spanish or Italian. No, but a machine learns something through its sensory input, through the machine learning algorithms. It can then actually share that data locally with another machine. So you end up having that quote unquote collaboration, if you will, obviously planned by the engineering team, right? But fundamentally, the machine now starts collaborating. So that data also is likely to be consumed locally. The data will go out, on the other hand, would include things such as maintenance information, energy consumption, maybe performance management, could even be some of the learnings that the machine obtained through its use, right? It's using, and then that information being useful for analysis later on can actually be shipped out. So most of the data is processed by the machine at the edge. In order to do that processing, you probably will not use the same tools, development tools, programming languages as you would for your system, the standard programming, right? So from a software point of view, we have to realize that it is probably higher level frameworks and languages that are going to be necessary. Apparently, data scientists prefer, 57% of them actually prefer Python, which makes sense considering the wide range of libraries and the ease with which one can leverage Python to manipulate data. Think NumPy, Pandas, Scikit, PyTorch. These are fairly easy to use frameworks to consume that data. So if you're used to consuming that data in an IT environment, you probably want to use it this way at the edge. Add to that TensorFlow, right? So obviously, we as a software company, we make sure that these building blocks, these tools are available in our real-time operating system, as well as our Linux environments. Now, one thing that is obviously not new, but that is becoming more common is a type of sensor input that I did not mention intentionally is a camera. So there's lots of industrial automation with cameras. There's lots of application with cameras, but cameras are becoming more and more uh, ubiquitous, if you will. They're getting cheaper. The quality is growing, and there is enough processing power to consume that video stream. So if you add to this framework something like OpenCV, and you marry all of that, suddenly you have a very strong foundation at the edge in your device to use the standard data you have in your processing, mix it with a high-level framework that your data scientists are very comfortable with, infuse some compute vision in the mix, and off you go. You have made your first artificially intelligent machine. You have all the tools to do that. And at this point, you might wonder, but don't you have some examples? So think about it. Assembly. If you have machines that are performing assembly, you can mix compute vision and artificial intelligence to do real-time course correction. You, as a machine picks apart to put it somewhere else, they're not always exactly in the same place on the conveyor belt, for example. So you would have that ability to do this. Another example could be packaging. You have a machine, let's assume you've ordered, a box of chewing gum, hairbrush, and a puzzle, and you have a variety of cardboard boxes to choose from. With compute vision, you can actually look at the volumes of each individual item and figure out exactly what the best box is for packaging, as opposed to relying on a person trying and probably doing it very good. The machine will just look at volumes and make a perfect analysis, like the Tetris, right? It's a Tetris puzzle. You could look at power generation and transmission, use cases where the physical model is being replaced by an AI model because we know that the manufacturing process, while extremely fine-tuned, is not perfect and may only be 99.99% close to the reality. But with an AI and machine learning system, the device could actually be progressively tailored to its actual physical representation in the real world. So there are just some examples, there's many others. What about that other 25%? So that other 25% of data, still going to be a lot of data, is going to be pushed out. It's going to go in transit, secure transit, I should say. So as this data is going to go from point A to point B, we'll have to make sure we choose the right stack to do that transfer of information. Because indeed, not all stacks are equal, and you want to adapt the protocol stack to the use case. And so when you're going to look at robot-to-robot communication, or artificially intelligent machine to artificially intelligent machine, you will have to really adapt to the need. So today, when it comes to this kind of communications, there are two protocol stacks that come to mind that are becoming more and more relevant. The first one is the time-sensitive networking, TSN. TSN actually is not a revolution, but most certainly an evolution of what used to be called AVB, audio-video bridging. And the spirit, if you will, was to make sure that if you send data from point A to point B, you want to have a guarantee that the data will reach point B, but most importantly, that that data will arrive within a certain time frame with a certain accuracy. And TSN gives you that. The hardware is ready. It's more broadly available. SoC vendors do include the technology in their hardware. out of the box, so it becomes much more available, much more widely available. So that's the first technology stack. The second one you want to consider is going to be OPC UA. So same as TSN, OPC UA is an evolution, but it actually allows you to have a vendor agnostic communication to communication system for the purpose of having machines talk to other machines. Great technology stack. Now, if you do send your data out there for other reasons, for storage, for further analysis, or even maybe sometimes just for to another machine because it's not as critical, you will use different types of protocols, maybe a little bit less involved. And I can think of about three. The first one being HTTPS, the most simple one, used in IT environment for a bunch of REST APIs and other environments. Very, very robust. And note that I mentioned HTTPS. Don't even bother with the non-secure version. And the other ones would be MQTT and AQMP. So having these stacks available will allow your robot to be very versatile and have this ability to communicate as necessary. So when I talked about offloading that data somewhere else, I mentioned local or remote, if you will. And when I said local, I emphasize other machines, but it can actually include local clouds. And again, if you go to a local cloud, you will use a type of protocols necessary for clouds. The advantage of a local cloud is going to be that you have the same infrastructure as your machines. So you can have a local cloud that is a bridge to another cloud. But at least it's local, so you have a higher level of control. And you actually, from a security point of view, may be a little bit safer if you do the things the right way, because you can limit the attack surface. When you go to a public cloud, the advantage is externally managed, and obviously you have a virtual unlimited scale off of this public cloud. Now, some might have more security concerns because this is externally managed, so you control a bit less. The nice thing also about this public cloud is they generally come with the right type of SDK available for your platform, whether it's real-time OS or Linux or something else. And so having these SDK makes that integration a breeze. So again, these are some of the options. Let's double click briefly on some other security aspects for your robots. Again, I mentioned some of the protocol stack. You heard me say HTTPS, for example. Again, always use security. I think now we all agree that it's critical. But what else could you do? Well, you can do a lot of things. So I will first repeat what I mentioned earlier. Again, security should not be an afterthought. So we've seen that from a comm stack point of view, you're fairly well covered. In most instances, you will be able to enable TLS as part of your communication stack. I would go as far as recommending to even ignore the non-secure use case for net new development and net new environment. I understand that it's not always possible when you do retrofits or when you have to insert a new machine within an old environment because of the reality of the environment, but it should always be secure by default. Anyways, as I said, what else can you do? Well, the first thing you can do on all your artificial intelligent machines is enable secure boot. In 2020, I don't want to be, patronizing, but you should have no excuse to not use secure boot. Every SoC that is recent that you can buy has the ability to perform a boot cycle that is fully secure. What that means is that your binary has been digitally signed. In some instances, you might even add encryption to it, so it's signed and encrypted. And when you flip the switch, only genuine software can actually start. That is important because this is what will anchor your root of trust. If you know you booted the right software, the only thing, and I put that in air quotes, right? The only thing left for you to do is make sure it cannot get tampered with once it's running. I'm not saying it's easy, but at the very least, now you know that when it starts, it's in a known state that is, what you can consider a secure state, or, at least as secure as can be. So please do that. Also, when it comes to having the data on your device, encrypt it. Always do that. And if you are not sure, I would say encrypt it, no matter what. And we talked about sometimes security being a compromise between, performance footprints and obviously security itself. I know that encryption requires a little bit more compute, but remember, one of the hypotheses and the things that we've seen happen in the market is that you have more compute. CPUs are faster today than they were last year, and they will be faster tomorrow. So use encryption, and there are some great algorithms that were created in recent years to actually help with this performance bottleneck. The one that comes to mind is Cha-Cha-20 and Poly 1035, which can be faster than the standard crypto that you see like AES, up to 3 times faster on some mobile platform without hardware acceleration. So there's been some very important innovation around security. So always encrypt your data when it's at rest. You could use either full disk encryption, and by disk, I mean it could be a USB thumb drive, it can be a micro SD card. It's essentially your mass storage. Or you can, if you want to reduce the processing time for this, to put your files into a file container, which is essentially an encrypted file system within the file, and then you can actually save your data there. So there are many options, so always do that. Another thing you can do is make sure you manage your software, and I'm going to use a term that I know is quote unquote hip, is microservice. If you design your application using an architecture that lends itself well to updates and management, then it's easier to update it and provide, patches to parts of the systems if you have to do that. And a good way to create, if you will, boxes that can be updated, units of deployment, I recommend you use containers. And we provide support for embedded containers. So not good container just for an IT point of view, but in VxWorks or Windows Linux, you can have these intelligent edge containers deployed, and then you can manage them, you can sign them, you can secure them. So you have this ability to create chunks of application that can be managed independently and secured independently. Makes your life a lot easier. Another aspect that is going to be important, we're talking about networking. And so sometimes your device, well, is rock solid, but what you can do is what attackers can do is they can do a denial of service attack on them. It's part of the CIA triad, confidentiality, integrity, and availability. So if you have a machine that becomes unavailable because it's under attack, then it can bring your system to a halt, even though in and of itself, the machine and the system is secure. So one aspect to help with denial of service attack is to leverage concepts that actually come from the avionics market, such as time partitioning. Let's assume you create your machine, your autonomous AI-enabled machine, and you want to make sure it doesn't get flooded by some network attack. You can decide that, well, I will allocate no more than 20% of my CPU time to the processing of the network information, so that you can actually control how much of your machine will dedicate energy to network processing. So at the very least, the machine can continue to operate even while under attack. And as a matter of fact, you can actually even know that under normal circumstances, maybe only 3% of the CPU is going to be used for networking. And if suddenly you get a spike and you even max out the allocated bandwidth, that can be a hint that there's something wrong. And then you can take action. So monitoring that thing will be very useful. One last aspect of security that I think is key and should not be overlooked today is privacy. And you might say, well, you know, privacy is not a right. And I know it's not a right, at least in our country. But the reality is privacy today becomes a key component of security. Medical devices may have a lot of private information that you may not want to see stolen. Your self-driving car, knowing wherever you go, you may not want to have that being available to the rest of the world. And it's not a matter of I have nothing to hide. I'm kind of in the same boat. It's more of a principle when it comes to these things. But when it comes to some types of private information, you want to protect them. And today, some legislation has been put in place in various geographies to address concerns around privacy. In Europe with the GDPR, and in California with the CCPA, right? So in your security consideration, do be mindful of privacy concerns. Now, we're talking about security. We looked at connectivity, the stacks, and some other things you can do extra on your device. Let's look at the options from a cloud point of view. What is it you potentially need? An edge cloud is obviously a cloud at the edge. And at this point, you may be rolling your eyes saying, thank you, Winura, for that. Uh, Now, joking aside, it all boils down to the definition of edge. Edge for Wind River and our customers, yourselves, has been in the last 3+ decades, the something that I call the electromechanical edge. So the machines that interact with other machines, humans, with the environment. I've heard the term cyber physical system used a few times. Now, in order to help these machines become more autonomous, leverage scale, all the knowledge that can be acquired throughout the entire system, local clouds, edge clouds are going to be necessary. Why? Because you will need high throughput and low latency. That is a requirement. So these requirements can become real and accessible when you have a cloud close enough. If you think of 5G as an enabler when there is no wire, then that's the perfect storm. You can put a lot of compute in this edge cloud, a lot of storage, and you have your best possible connectivity between that robot and that cloud. So anything that can be processed at this edge cloud will have the ability to be processed there. And obviously, it's a little bit more secure in the sense that you have more control over it. Allow me to take a step back here. If you look at what Wind River has been working on in the last 30+ years is platforms. We provide software platform for this electromechanical edge I referred to. You've known VxWorks, then Linux, and a variety of tools we provide, to help you design this robot. And now we're going to the next step by making sure that you have all the right software blocks to create these artificially intelligent machine. We mentioned things, about AI, Python, TensorFlow, OpenCV. We talked about security, all that good stuff. And now I'm going to the edge. Why does it matter? Because as I just said, the edge is no longer just machines. It's an ecosystem of machines. And this edge will require its own clouds. And as I just mentioned, this cloud will have some level of service that's going to be necessary. Like I said, high throughput, low latency. And so Wind River, looking at the problem set, realized that we need to expand the offering to enable you to create this next generation and environment. And so we have introduced recently the Wind River Cloud Platform, which is a 6.9 hardened edge cloud. And just like the rest of the Wind River portfolio, it is a platform that you can actually configure to your need. You can control it, you can tailor it. And this is really where you start having the value and the DNA of Wind River that is available from that electromechanical edge all the way to that edge cloud with the ability to expand to these hyperscale public clouds if you choose to do so. So now you can enable more services at the edge. Some data, as we discussed, can be and will be processed in the machine. But again, that remaining data for all these other services will be processed at this edge cloud. Again, I'm going to repeat things such as predictive maintenance. You could look at overall factory optimization, performance management. How about, emergency services? Think of the highway of the future, where you will have local clouds in various parts of the nation on some freeways that will control some of the information to be aggregated. Imagine a number of clouds you need in LA, right? Every freeway, the 405 cloud, the 5 cloud, the 10, the 110. So you would have all these local clouds. And these are just examples, right? So again, our goal is to enable you to create this next generation of artificially intelligent machines. Well, this is the end of the part where I am talking, and this is where the more interactive part of the session begins. But first, I wanted to thank you for your time, for your patience, for listening. I hope this was informative, at least as fun as it was for me. I wanted to share with you some of my insights and some of the bets Wind River is taking today, where we're going, where this wonderful world of artificial intelligence and machine merge. And, there's always new stuff coming up. So if you do want to share some of your thoughts with us, please do so. My virtual door is always open. And being in product management, I welcome your insights to help us be better versions of ourselves. Now, having said that, let's look at questions, if any. Please don't hesitate. Everything is fair game. Again, thank you very much.